Hey guys, welcome back to the Science Factory. I'm Brian, and today we're going to be learning about earthquakes and fault lines. Now, for today's experiment, you're going to need some cardboard, a bowl, some flour, a measuring cup, and I recommend that you get a cookie sheet, just so that it's a little bit less messy. Before we get to the experiment part, I wanted to talk about what faults are and what the different types of faults are. So the Earth's mantle makes up about 84% of the Earth by volume, and the core makes up 15%, which means that the crust that we live on is only 1% of the Earth's material. We believe that the Earth's mantle is solid, although we've never actually seen it because we can't dig all the way down to the mantle. But even though it is a solid, it behaves kind of like a very viscous or thick liquid. And this is because it's so hot that the rock can deform over time and it acts more malleable, like a hot plastic. Now, the crust of the Earth is made up of something called tectonic plates, and these tectonic plates kind of float on the mantle, and they move around on the mantle due to the convection currents or movement of the mantle. Because these plates are floating around on the mantle and bumping into each other constantly, there's a lot of different kinds of movement they can have. They can slip past each other, they can bump into each other, or they can even pull apart from each other. It's almost like a big game of bumper cars, but each bumper car weighs trillions of tons. The boundary between these tectonic plates, where all of the motion happens, that's called a fault line. Most plates move at about the same speed that your fingernails grow, and the fastest plate in the world races along at 6 inches a year. Whew! Super fast. When the plates are moving smoothly, we don't really notice it as much. Wait, wasn't my house 15 feet to the right? But sometimes they can get caught and move suddenly, and that's what causes earthquakes. Sudden movement of the Earth's plates to a new location. Now, there's definitely a lot more to learn about tectonic plates, and they're super cool, but we're gonna have to save that for a future video, because right now I want to talk about the different types of faults. To explain these faults, I'm going to use these two triangles as a visual, but I want you to imagine that this is just the edge of each tectonic plate. So this tectonic plate extends for hundreds of miles that way, and this one extends for hundreds of miles that way. Which means that both of these tectonic plates are pushing against each other with tremendous amounts of weight and pressure, or they might be pulling away from each other with tremendous amounts of weight and pressure. Because remember, we're talking about the Earth's crust. It may only be 1% of the Earth by volume, but the Earth is pretty big. So these are very big chunks of rock that are slamming into each other, grinding past each other, or pulling apart from each other. And there's a lot of force involved. Now, the tectonic plate that rests on the bottom is called the footwall. And it's kind of easy to remember because the base of it here acts like a foot. And the one that's on top of it is called the hanging wall, which again is kind of easy to remember because it's kind of hanging off of the other one. And the line in the middle is called the fault plane because it's the boundary between the two tectonic plates, which again, remember, is called a fault. So, what types of faults are there? Well, there's three main types that we're going to be talking about today. The first type of fault is called a normal fault, and these are found at divergent plate boundaries, meaning that these plates are moving apart. And in this case, the hanging wall slides down the footwall and exposes a section of cliff that's actually part of the fault plane. In this type of fault, the tectonic plates are experiencing tension because they're being pulled apart, which is why the hanging wall is sliding down the footwall. Now, interestingly, there's a rare type of fault called an oblique fault, and oblique faults are just like normal faults, except that when they diverge, the hanging wall doesn't slide down and it instead leaves a gap. Now, our second type of fault is a reverse fault, and as you might expect, it goes in the reverse direction of a normal fault. If you've heard of a thrust fault, this is actually a type of reverse fault. Reverse faults take place at convergent boundaries, which means that the two tectonic plates are moving together and one of them is lifting to higher elevation. And this is how we're going to see mountains or hillsides formed. This happens because as the two tectonic plates collide, the hanging wall is pushed against the footwall and uplift occurs. The community college that I attended before university was actually built on one of these types of faults. And because it was on a reverse fault, the entire college was lifted up above the surrounding land. Pretty neat. The third and final type of fault that we'll be talking about today is called a strike-slip fault. And in these faults, the two plates are sliding alongside one another instead of pushing apart or together. These types of faults tend to occur near transform boundaries, and they're not very common on land, but they're common in the ocean, which is where seafloor spreading occurs. Seafloor spreading is when two oceanic plates are moving apart and magma comes up through the crack that forms and forms new oceanic crust. Now, as a result of these divergent plates, the plates that are next to them are going to have slip faults. So as these two plates move apart, there are two slip faults formed here and a divergent fault formed here. Alright, so before we get to mixing our flour and water together for the experiment, I wanted to show you a simpler version with paper. First, I'm going to cut this piece of paper in half, and then we're going to create two different types of faults. For the first fault, I'm going to cut a pretty straight line all the way across the paper. It can have a little bit of wiggles in it, but it's going to be mostly straight. For our second one, I want to cut much more jagged of a line. Now, for this fault, we have a relatively straight line, so there's not going to be very much friction. And if we had two plates that were slipping past each other, a slip fault, you can see that there is some bulging, but for the most part, it's a pretty smooth motion. However, for our other fault, that's not going to be the case. On this model, we would expect that there's going to be a little bit more friction. So as the plate tries to slip past itself, it can catch, and that energy can be released suddenly in an earthquake. Real faults work more like this fault here. Lines don't tend to be perfectly straight in nature, and our fault lines can get caught on each other as they try to slip past one another. The first thing we're going to do in this experiment is make our earth. And our earth is going to be made out of flour and water. This is why we're using a cookie sheet, because this part gets kind of messy. Now, I'm using a whole cup of flour because I want you to be able to see this at home. But in person, you can pretty easily do this with just half a cup and maybe even a quarter of a cup of flour. Next, we want to add about the same amount of water. You don't want your final mixture to be too runny or too dry, or it's not going to work right. So what you want to do is add water until you don't see any dry parts left and the whole thing is a uniform consistency. Let's go ahead and add some water. We're going to add a little bit at a time and stir in between. As you're mixing, make sure that you don't just mix the middle and scrape the sides of the bowl to get all that dry flour back in and fold it together. I like to make a lot of pancakes. This is actually a pretty similar process, so if you've made pancakes before, you're ready to roll. So I'm going to stop here just for a moment so you can see some parts of this look like what we want, but other parts are still completely dry. So we're going to add a little bit more water. This is what it should look like once you're done stirring. I didn't add very much water, and it's actually almost clean to the touch. Not too goopy. Now you'll notice with this consistency, when I take it out of the bowl, it wants to stick to itself instead of the bowl. That's one way that you can know that it's at the right consistency. For our next step, we're going to cut a fault line right down the middle. Now I know that I said natural faults aren't a straight line, but we're actually going to make this a straight line so that it's easier for us to see what happens to the flour later on. Alright, and now for the fun, messy part. We're going to put these all the way together, and then we want to lift one just slightly over the other so that there's a little bit of an overlap. And we're going to spoon on some of the guck that we made. Alright, so for our first fault, we're going to observe subduction. And as I push these two plates together, you should notice that the earth on top starts to form a taller and taller mountain, and this earth is lifted upward as the plates converge. Whoa, pretty cool! You can see how a mountain would get much bigger over time as the plates come together, and all of that earth is pushed upwards on top of the two converging plates. Whoa! Pretty cool. You can see as this one advances that the front of the mountain doesn't move too much, and you can see some of the stresses start to form. Awesome. Now we're going to try a slip fault where the plates are moving parallel to each other in opposite directions. I want you to watch closely for striations or lines on the top that show the movement of the plate as the land stretches and tries to take its new shape. You can see it's starting to stretch out here. And it's tearing here and forming a sheer cliff over here. This is how we might end up with two mountain ranges with very similar makeups that are on different plates. Now, if you're not getting very good stress lines along the top as you move the two plates, one thing that you can do is plop all of the flour mixture onto the cardboard like this and let it sit for about 10 to 30 minutes. A skin will form over the flour and you'll be able to do the same thing, but you'll see the stretching much better. So we're gonna show this one more time, and this time I let it dry for a while before we tried moving them. So watch, if I touch it with my finger, it comes off clean. So because there's a skin over this mixture, when I pull these plates past each other, we should see better lines on the top. You can play with different consistencies, different speeds, and different drying times to see what gives you the best continental crust. All right, let's go ahead and try it. 3, 2, 1. Whoa! We can definitely see evidence of continental drift this time on the surface. Look at these lines. As we keep going, we should see the lines continue to elongate, and we can really see the surface stretching here, just like we see in real life with the actual continents. Let's keep going until the fault completely slips past. Wow, that was pretty cool. I was really excited that we saw such good lines on the top. I let this one dry for about 15 minutes. So who knows, if you do it for longer, you might have even better markings on the top, or it might start to harden. Please make sure to let us know how it went for you in the comments down below. Well, that's it for today's experiment. Please go ahead and subscribe and hit the notification bell so you don't miss any of our future videos. We upload every Monday, Wednesday, and Friday, and we will see you next week. I don't know about you guys, but I get super nervous during earthquakes. I just start shaking uncontrollably. What is the safest place to be during an earthquake? The stationery store.